Thanks.
So, welcome everyone back, and we have the third lecture by Roland Bauerschmidt on Log-Sobolev inequality and renormalisation group.
Okay, thanks everyone for coming back. Let me quickly go through what we discussed the last two lectures. So first of all, we're looking at this type of continuous Glauber dynamics given as here. Our goal is to study statistical mechanics models of the type of either lattice models or continuum models, and we'll be focusing on the continuum models. We'll get back to this very soon. And then last time we discussed, so in the first lecture still we discussed this very classical and beautiful result of Bakri-Emery, which gives a criterion for the Log-Sobolev inequality, which is a convexity assumption, which is unfortunately in the cases of interest in statistical mechanics is almost never true. And so last time I explained the strategy to get around this, which is by looking at a different semigroup rather than the original Glauber semigroup that we're interested in. So remember, we're interested in studying the dynamical relaxation of the Glauber dynamics, which can be encoded in that functional inequality, the Log-Sobolev inequality. And to prove that Log-Sobolev inequality for the Glauber dynamics, we may use a different dynamics. And so this dynamics is this renormalization group dynamics, which is given as follows. We have a decomposition of a Gaussian measure. So we start with a decomposition of a covariance matrix CS, which is in our case going to be the Green's function of Laplacian. We write it as an integral over infinitesimal covariance matrices, which in our case are going to be heat kernels. So the choice we'll be making is that C dot is e to the minus SA, and A is a matrix which you should think of as an approximation to the heat kernel, or to the A is an approximation to the Laplacian, so e to the minus SA is a heat kernel. So in particular, the Gaussian measure with covariance C infinity is just a Gaussian free field. Then we discussed the renormalized potential, which was given by taking, Vs, the renormalized potential Vs was defined by through its exponential. So e to the minus Vs is defined as the convolution of the Gaussian measure with covariance Cs with e to the minus the original potential, e to the minus V naught. And we discussed that equivalently, that means that V satisfies this so-called Pulzinski equation, this equation for V, which you see in the middle of the slide, which has as a first term a kind of a diffusion term, but be careful, the coefficients of this Laplacian, they change with time and they become increasingly smooth in space. And then there is a nonlinear, Hamilton-Jacobi type nonlinearity. Okay, so and then what we proved is that if we can bound the Hessian of this renormalized potential from below by some constants which don't have to be positive. In fact, the whole point is that they can be negative. Then we can still get a Log-Sobolev inequality with the constant given in terms of this integral. And this condition was just such that if we start with a convex potential, we exactly recover the Bakri-Emery result. But we can look at non-convex potentials, such as the ones appearing in the statistical mechanics models we're interested in, and then still get a bound on the Log-Sobolev constant. So okay, so and then we proved this, and the proof was very similar to the Bakri-Emery proof, except that we used throughout the whole proof this different semigroup, and still ultimately obtained the Log-Sobolev inequality for the Glauber semigroup. So So there's the subtle point somehow that we're interested in this relaxation of the Glauber dynamics, and we can switch to a different dynamics to prove that, and that was the somehow the main point. Okay, so then I gave you a homework exercise, which is to check this criterion in a somewhat simple finite dimensional class of examples. As again, let me emphasize again, I'd be curious to see some nice solutions to this. But in the remaining 2 lectures, what I will discuss is an example from the second slide, which is the continuum version of the Sine-Gordon model. So let me start discussing and defining this model. Just this. So this is the this is the continuum Sine-Gordon model. So we start with a finite grid. So let's take a box which I'll take to be a finite torus, and with a mesh of I guess you can finish the remaining dots, but so there's we're taking this box which has this grid of mesh size epsilon, and the whole torus has length L. So that will be our approximation of R2. And I will often denote this torus by omega epsilon, which is given by, say, the 2-dimensional torus of side length L intersected with the grid of width epsilon. So this is a finite dimensional set, and we'll be interested in taking, in particular, epsilon to 0, but also in principle in taking L to infinity. Okay, so then we have a finite set. So this is a finite dimensional space, and so we're in the setting of the previous lectures, and we can define the Sine-Gordon measure, which is defined as follows. So there's a proportionality constant, which I will not write down, and then the measure is, as the usual form, is exponential of maybe I'll put an L here as well. There is a sum which I've normalized the appropriate normalization for an integral. And then we have the usual free field term. And we'll also put a mass term. So let me. And then we have the Sine-Gordon interaction, which is a periodic potential. And as I'll explain, to define a non-trivial measure or non-Gaussian measure in the continuum, you need to put this divergent counter term epsilon to the minus beta over 4 pi. And beta appears inside the cosine. Okay, so this is the continuum Sine-Gordon model in the lattice approximation. Now, I've mentioned this before, but let me mention it again. This is the normalization or the choice of the coupling constants I've made here, which is, for example, this divergent counter term and the normalization of the sum by the lattice width epsilon squared. So this is the appropriate normalization for the continuum model to get a non-Gaussian measure as epsilon goes to 0 in the continuum. There's also the lattice Sine-Gordon model, which is by no means less interesting, perhaps on the contrary. so you may argue, well, this is a lattice model, how I defined it. So isn't this the lattice Sine-Gordon model? No, it is not. The lattice Sine-Gordon model differs by the choice of the coupling constant. So for the lattice Sine-Gordon model, you wouldn't put the epsilon squared in front of the sum. And you also wouldn't put the divergent counter term here. And all of this changes it changes the kind of area you're interested in. So it changes the size of the coupling constants, for example. And okay, so let me leave it at that. I just want, it's a good exercise if it's a bit confusing to go through these rescalings and see how one normalization is related to the other and how these models are different. I'll come back to this in a little bit. So, but anyway, so this is the continuum Sine-Gordon model. Okay, so what I should mention next is to say that, okay, actually as epsilon tends to 0, it is known that this measure does converge to non-Gaussian measure in the continuum, at least under certain assumptions. So I don't want to be too precise about this. So let me summarize this as follows. So in various works, and I'll give a few references in just a second. And again, and this is also under varying assumptions. Under varying assumptions on beta, z, and m. So it is known that, roughly stated, for beta less than 8 pi, strictly less than 8 pi, the limits epsilon to 0, and let's say some L to infinity under more restrictive assumptions exist, and define non-Gaussian, so in the quantum field theory terminology, non-trivial measures, and also that these measures have a bunch of properties that are of interest, such as reflection positivity and so on, which we will not need and which I will not discuss. Okay, so this is what is known. So this is justifying the normalization I've chosen. At this point, I should also maybe can fit this on the slide because it's maybe I'll move this here. So there's this condition beta less than 8 pi. So you might wonder what happens at 8 pi, and I don't think this is a theorem, but I might be wrong. So if someone knows better, correct me. I expect that all continuum limits that you can obtain, and by that I mean you choose any coupling constants you want, not necessarily the epsilon to the minus beta over 4 pi. Are expected to be Gaussian. Okay, so this is what is known and expected, and so you can already sort of see a vague hint of similarities. Well, you can see that at least the beta equals 8 pi case or greater than 8 pi case, that kind of looks like 5, 4 in dimension bigger than 4. And in fact, there is a sort of a vague correspondence in terms of how many counter terms you need to construct these measures. So comparing with the phi-4 model, beta roughly plays the role of dimension, so the role of D. In the sense, with the correspondence that you can construct the Sine-Gordon model when beta is less than 4 pi. So beta less than 4 pi for Sine-Gordon. Similarly, as you might construct the phi-4-2 model. That once you cross the threshold of 4 pi, things get a bit more subtle. And it looks a little bit more like phi-4-3. In the sense that there are additional counter terms that are required. And then that beta, once you reach 8 pi, well, we expect that any limit, so in terms of scaling, or it's marginal, and we expect that any limit is Gaussian, just like phi-4-4. Okay. So in fact, beta, unlike the dimension, or at least the dimension in the strict sense, beta varies continuously. And in fact, there is an infinite sequence of thresholds. Oh, there is a couple of questions. Does it have a phase transition at 8 pi? Gaussian for some z and non-Gaussian for another parameter. Okay, so Milton's question, I don't think, not that I'm aware. At least what I would expect is that above 8 pi, it's okay. Let me postpone this question. I'll think about it in the break and give a maybe more precise answer. You might have a point there. I'm not sure. At least I don't think anything in that direction is known. But I'll give some more explanation of what you might hope in the break. And then there is Tyler's question. Is there an intuition analogous to the semantic random walk intuition for phi-4? I don't think so. I mean, somehow, this, to a certain extent, the Sine-Gordon model looks a little bit more like a rotator or like a two-component phi-4 model. I guess for that, you would have a representation. But I'm not aware of any useful geometric representation for the Sine-Gordon model, but that's certainly a very interesting question. I don't know. Okay, so okay. In fact, there is an infinite sequence of thresholds that one encounters in the construction. So what do I mean by that one encounters? Well, there's increasingly many counter terms that need to be accounted for, just like if you were going up to d is equal to 4 in a phi-4 model. And these occur at these values. Beta n is equal to 8 pi and I guess 1 minus 2n or something like that. Since this, as I will explain shortly, the Sine-Gordon model has a lot to do with the model of a Coulomb or Yukaba gas, and also otherwise, it's a model for a quantum field theory parametrized by this parameter beta. So you might wonder if these thresholds have a physical meaning in terms of either of these interpretations, either in terms of the interpretation of quantum field theory or in the interpretation of statistical mechanics of the Coulomb gas, which we'll get to shortly. And The answer is, I'm not sure. I don't know. But to the extent I understand, the consensus appears to be that these thresholds have no physical meaning whatsoever. So in the sense of the Coulomb gas, which we'll get to, that means there are no transitions of any thermodynamic nature happening at these thresholds. And I suppose at the level of the quantum field theory, I guess it would also mean that I mean, all quantities like the mass spectrum and so on are expected to be analytic throughout all these thresholds. So that really there's no way in which you would interpret these thresholds as phase transitions. They appear to be a mathematical artifact of the way we think about the quantum field theory here. Okay, so anyway, so let me just write this down, not too precisely so that I can't be quoted. So the physical meaning of these thresholds remains debated. But the consensus among experts, physicists, appears to be that they have no physical meaning. That of course, on the probabilistic side, you can see them, but in the physical meaning. Okay. Okay, so all right. I should perhaps also mention that there's really quite a lot of very precise conjectures about the Sine-Gordon model. So they usually refer to the massless limit. So here I'm always keeping this mass parameter, which is assumed to be strictly positive. But once you pass to infinite volume, or you restrict to gradient variables or so, you can make sense of the massless limit. And there are a lot of very explicit conjectures for the mass spectrum and other things with very interesting behavior that are made in the physics literature by people like Zamolodchikov and so on, which are quite intriguing, but I'm not going to get into any of this here. Okay, so so the next point I want to mention is that in fact the Sine-Gordon model has a very close relation to the Coulomb, or if you allow the mass parameter, that would be the Yukaba gas. So this is also called the Sine-Gordon transformation. And so this goes as follows. If we take phi to be a Gaussian field with covariance given by the Yukaba potential, which is the Green's function of the massive Laplacian. And let me just put an epsilon here, as I always do. So this is the Yukaba potential. So if m goes to 0, it becomes the Coulomb potential. Then you can compute the Fourier transform of the field, or let me take the Fourier transform of sum from I to n of phi xi sigma I. And well, it's the Fourier transform of a Gaussian measure. So this is just given by e to the minus beta over 2 times the sum for ij, sigma j, c, xi, xj. So so plugging in the, so you see this is just the Gibbs factor for n charges with positions xi and charge sigma I. So sigma will be plus minus 1 for me. So it's sigma I. And the interaction is the Yukaba interaction. Now, if you go to the continuum, well, the Yukaba interaction is not defined on the diagonal, right? So as epsilon goes to 0, the diagonal term here will not will blow up, but you can put it on the other side. And if you do that, so that would be taking e to the beta over 2 times C00. So I'm assuming we're on a torus here, so C00 is the same as CXX. Sum I is equal to 1 through n phi xi sigma I. So this is then just given by the Coulomb interaction without any self-interaction. So what this does is it just takes out the term I is equal to j, right? Okay. Now, for the 2D Yukaba potential, well, we know how the Green's function behaves on the diagonal, right? So the Green's function on the diagonal blows up logarithmically, like 1 over 2 pi log epsilon plus, I guess this would be log epsilon inverse, plus some constant, which depends on the mass, plus little o of 1, as epsilon goes to 0. So this factor that we took out, e to the beta over 2 C00, is just a constant times epsilon to the minus beta over 4 pi. Okay, so so this term here, so let me highlight this here. It's just this e to is essentially up to a constant, just this e to the minus beta over 4 pi. And so this is the Coulomb energy, or the Gibbs factor for the Coulomb energy of n charges with positions xi and sigma I. And what we can now do is we can take the partition function, or the grand canonical partition function of a Coulomb gas, which involves this Gibbs factor, of course. So once we take the partition function of the 2D Yukaba gas, so that would be the Yukaba gas partition function is, well, you sum over, there's n particles, they have activity z to the z, so we have a factor z to the n divided by n factorial, and then we have the position of these n charges which we're integrating over, so that is x1 up to xn, it's an omega epsilon, and sigma 1 up to sigma n is in plus minus 1. So this is the position summing over all possible charges, and then we have the Gibbs factor e to the beta over 2, sum I, let's say not equal to j, sigma I, sigma j minus Laplacian. Okay, so this would be the partition function of a Yukaba gas at temperature beta and activity Z. So this also explains the square root of the beta that I put into the definition of the Sine-Gordon model, because it becomes the beta of the Coulomb gas, or the Yukaba gas. I'm going to be slightly imprecise with that terminology here. Now we substitute in that Sine-Gordon representation, and what we find is so that is, oops, the Sine-Gordon representation is to write this as this expectation of the Gaussian with the I. So I'm plugging that in. So we have to put this divergent prefactor C0, 0, n. So remember, this is the essentially epsilon to the minus beta over 4 pi. Then I'm summing over the positions and charges. So I'm going to use the abbreviation that xi I stands for xi sigma I. So I'm summing over all charges, and then I have the factor e to the square root beta, sum from I through n, phi xi sigma I. Well, now we notice that this sum here is really, it factorizes, right? We have a sum over n variables, xi n up to xi n, and then we have a product of these of terms associated to these variables. So this is equal to epsilon squared, sum over a single xi, which is, remember, that's just x sigma. Then we have e to the I square root beta, and then we have a phi x sigma, and the whole thing to the n. And well, that is equal to epsilon squared. Then we have the sum over x, and we can write this as 2 cosine square root beta phi x. One more bracket to the n. Okay, so and now we see that, well, in fact, we have the sum over n, z to the n divided by n factorial, and then all the other terms that appear are just some number to the power n. So this is really an exponential. So we have the exponential of 2z, or let me write it like this, epsilon squared, sum x is an omega epsilon, then we have 2z, then we have this, oops, it's the wrong, this term, so okay, so epsilon, oops, epsilon to the beta over 2 to C0, 0. So remember, this is essentially epsilon to the minus beta over 4 pi. And then we have the cosine square root beta phi x. Okay, so we've seen the partition function of the Yukaba gas in 2 dimension equals the partition function of the massive Sine-Gordon model. And indirectly, we'll be using this correspondence to understand the Sine-Gordon model very soon. Okay, so, okay, good. So this was a little digression that explains one of the, well, it explains this duality between the Sine-Gordon model and the Coulomb gas. This, in fact, this correspondence has, in fact, been used. So we'll be using it sort of to study the Sine-Gordon model. We're interested in the Sine-Gordon model, but this correspondence can be used in both ways. And in particular, Fröhlich, for example, has used it in very clever ways to get good estimates on the Coulomb gas by going through the Sine-Gordon model and so on. Okay. So, okay, so back to the Sine-Gordon model. You may forget the Coulomb gas for a while. Going back to the previous lectures, well, what we're interested in is the Glauber dynamics of the Sine-Gordon model. So this doesn't really have anything to do with the dynamics of the Coulomb gas, right? It's the Glauber dynamics of the Sine-Gordon model, or also called the dynamical Sine-Gordon model. So this is this is the following system of SDEs. So we have this divergent, I guess there's a square root beta, I guess. Perhaps this is a plus because we've differentiated cosine. Doesn't really matter since z, the constant z, is allowed to be real valued. So sine square root beta phi. And then there is noise, which may be square root. Okay, so this is the Glauber dynamics SDE associated to this model and what we discussed before. And let me be a bit explicit here. So here, W epsilon is a standard Brownian motion with respect to the inner product that is normalized in the continuum fashion. So, so this is a discrete version of space-time white, discrete in space. So this is a discrete version of space-time white noise, if you like. And so in the limit epsilon goes to 0, this is what was studied by Howe, Martin, and AJ. Not with a lattice regularization, but with a smooth cutoff. But from what I understand, that is there's a technical difference there. But I don't expect that that this would cause serious difficulties to instead look at the lattice regularization. So they studied. They constructed the limiting dynamics. So the limit is well posed in fact, for all beta up to 8 pi. So in the what would be the optimal regime for beta. So what we'll be interested in something slightly different. We'll be interested in the long time relaxation, so the Log-Sobolev inequality for this model. We won't be able to go up to 8 pi, but only up to 6 pi. So that's so remember in the correspondence at 4 pi, up to 4 pi, the Sine-Gordon model looks a little bit like 542. So we can go one threshold further, but not all the way up to. We'll also not take the limit epsilon to 0, but we'll always keep epsilon fixed, but arbitrary. And the goal is to obtain estimates which are uniform in epsilon. So that just saves us some technical work that one would have to do to take the limit, but okay, so we'll keep epsilon 0, but we'll derive estimates that are uniform. And okay, so
sorry, Roland, there is a question.
There is a question by Rich. What about as volume goes to infinity? Yes, what about it? So what exactly is your question? So your question is, what about as volume goes? Do you have estimates independent of the volume? If the coupling constant is small, we have estimates independent of the volume. If the coupling constant is not small, we don't. That, in fact, is probably an interesting problem to try to get those, which I believe should be true. If you have a mass term, I guess they should always be true then. But that's a good question. I'll get to the statement and maybe after the break, but I'll explain. Before the break, let me just mention that the correct normalization of the Dirichlet form is, so I'll denote this Dirichlet form by d epsilon of f is s, has this 1 over epsilon squared term here, which corresponds to the normalization of the Brownian motion w epsilon. So the Dirichlet form is going to be this is the Dirichlet form corresponding to this dynamics. And okay, so I guess there's only 3 minutes left. So maybe I will take the break 3 minutes early and resume 3 minutes early. And then after the break, I'll tell you what we prove and how we go about this. If that's okay to take the break now.
So yeah, I think it's fine. I mean, yeah.
Okay.
Questions?
Do you have the slides for last lectures?
They're on the website, I think.
They are.
I think they're still labeled slides 1, but I only have one file that contains all slides. So I think I checked it and they seem to be up, but it's called slides 1. So anyway, it's all in the same file.
Okay, thank you.
Maybe, Milton, I mean, so maybe we can take the break now, but Milton had a question about the critical case. And if you're interested, I can try to answer this now, but this is not, this is maybe too vague for everyone's interest. It's more of a guess, what you might expect there.
I can switch off the recording and then you can answer it.
So, okay, so back to the Glauber dynamics of the Sine-Gordon model. So what I try to prove in the rest of these lectures is this result on the Log-Sobolev constant. We restrict to beta less than 6 pi. No R2. M positive, L positive. Then there is the Log-Sobolev constant gamma, which a priori depends on all these parameters, beta, z, m, l, but it's strictly positive and independent of epsilon. Such that the Log-Sobolev inequality holds. So the entropy with respect to the Sine-Gordon measure regularized using a lattice of mesh epsilon is bounded by the Fisher information as follows. And then to answer Trish's question, under the additional assumption that the coupling constant is small, or more precisely, if m to the minus 2 plus beta over 4 pi times z, absolute value z, is small, so it's less than maybe some delta that may depend on beta, then we get an estimate that is uniform in the volume. So gamma is bounded below by, in fact, m squared plus order e to the beta over 4 pi times z. And so this is, may depend on beta, but it's independent of L. Okay. I will only remark that you can, in fact, also get an analogous result for conservative dynamics. And so here the Dirichlet form is, maybe I'll put a 0. So you have to normalize by 1 over epsilon to the 4 rather than epsilon squared. And then you sum over all pairs of nearest neighbors on this fine lattice of mesh size epsilon. And you take the usual Kawasaki Dirichlet form, and the statement is very much analogous. So here we consider the measure. The measure is the same one as before, except restricted to a plane of where this restricted to where the sum of all spins is constant. And then there's a result which is very much analogous to the one I stated above, in the sense that for all finite choices of parameters, there is a uniform and epsilon Log-Sobolev constant, and under the assumption that the coupling constant is the same assumption that the coupling constant is small, the Log-Sobolev constant has the scaling that you would expect, which is not independent of L, but there's an additional 1 over L squared on the right-hand side, which is the typical scaling of the spectral gap or Log-Sobolev constant for Kawasaki dynamics. And in fact, in the proof, it doesn't really matter whether we consider the Glauber or Kawasaki dynamics. This is something that anyone who's otherwise looked at Kawasaki dynamics before is always surprised about, because usually it's much harder to study the say Log-Sobolev constant for the Kawasaki dynamics. The reason that it doesn't really matter in our proof is that basically we need to understand the invariant measure extremely precisely anyway. So, so it doesn't really matter whether we have this restriction to the hyperplane or not. On the other hand, when you usually study Glauber dynamics, say for IID spins, then whether they're truly IID or IID up to the global constraint that the sum of all spins is 0 is a huge technical difference. But we have to decompose the measure anyway, so it doesn't really matter. Okay, so.
Hey, Roland, there are 2 questions in the chat.
2 questions, yes. So, okay, first question: do you have integration with respect to the measure Indeed. Otherwise, I guess it wouldn't be true. The statement would be, so thank you. And the second question is, do you also have an upper bound for gamma? I'm pretty sure you could get it. We haven't, it's not some, I'm pretty sure from the construction that I'll show you, you can also get it. I mean, it's I don't, okay, so I don't think it would be an issue to get it, and somehow, so this is the spectral gap that you'd get for the free field, and it's, okay, so I don't think it would be a problem to get it, but we did not look at that carefully. Okay.
But for this, couldn't one just pick a good test function like the one you would
exactly. You pick a test function, and then you have to evaluate the test function, and that would not be a problem using what I'll show you. So indeed. Okay, so all right, so I'll show you the proof of this result, at least completely for beta less than 4 pi, and then depending on how much time there is. So let me start with, I guess I have discussed normalization quite a few times, but somehow to me this is an important conceptual point, and one that can cause a lot of confusion. So let me do it again, or let me. So we want to take, so we want to apply our theorem for the Log-Sobolev inequality. So we have this potential V, which is epsilon squared times sum over epsilon. And then we have 2z epsilon to minus beta over 4 pi cosine square root beta phi x. Okay, so this is what I call the macroscopic normalization. We normalize the sum as an integral, and then the interaction looks singular, right? We have this epsilon to the minus beta over 4 pi. So we have this, from the macroscopic point of view, we have a singular interaction. But we could also normalize from the microscopic point of view. So this is more like what Hugo, take a point of view that Hugo is taking, right? So we just have a sum over the points, but we don't normalize it by epsilon squared. Well, then we have a coupling constant, which, well, looks much smaller, right? It's epsilon to the 2 minus beta over 4 pi. So this is the microscopic normalization. So this Sine-Gordon interaction looks very singular from the macroscopic point of view, but it looks very small from the microscopic point of view. So the lattice Sine-Gordon model is one where you have a microscopically coupling constant of order 1 rather than a small one. So correspondingly, so of course these points of views are completely equivalent, but so correspondingly, the interaction A, which is minus Laplacian plus m squared, when we pick the macroscopic inner product, so this is the say uv epsilon is epsilon squared times the sum over. So again, this is macroscopically normalized. So it looks like a continuum Laplacian with a mass of order 1. But equivalently, we could normalize microscopically. Then we'd have unit lattice Laplacian. We'd have a mass which is tiny, so it's epsilon squared times n. So this is again the microscopic point of view. So in the macroscopic normalization. So this corresponds to this is where you get the SPDE as epsilon tends to 0, and the microscopic one is more like you have some kind of a particle or lattice system with weak interaction. Now, of course, these 2 points of view are completely equivalent. And arguably for this model, it's the macroscopic normalization that is probably a bit more natural. But I'll pick the microscopic one anyway, because Thierry and I, we come more from lattice systems or statistical mechanics rather than quantum field theory and PDEs. And so for us, the microscopic normalization is a bit more intuitive. But I expect that for most of you, it's going to be the other way around. Anyway, these are completely equivalent, and you can pick one point of view you like. You choose to study a system on the unit lattice with a tiny, with a small interaction, epsilon to the 2 minus beta over 4 pi, or you pick you look at the problem in the continuum with a singular interaction. So these are equivalent points of view, but we have to pick one, and I pick the microscopic one. Okay, so. But it's I mean, it's worth translating between these every once in a while to see what's going on. Okay, so that's what we want to do, and so the first step is we go back to the well, we want to go back to somehow the Yukaba gas, well, the Yukaba gas will appear somewhat indirectly. But I'll call this the Yukaba gas representation of the renormalized potential. And in some form, this is underlying all works on the Sine-Gordon model in some way. But really, the way I formulate it here was very nicely done by David Bridges and Tom Kennedy. Okay, so we want to look at the effective or the renormalized potential VT, which is supposed to be a solution to the Pulzinski equation. So we want to understand VT of phi. Now we write it as this as follows. So I like to think of it as some kind of infinite dimensional Fourier series. So V is a sum from n is equal to 0 to infinity, and these functions Vn are given as follows: Vn t of phi. I'll put a 1 over n factorial here, accounting for the fact that I'm summing over. And then I'm summing over charges x1 up to xn with charge plus minus. So these are an omega epsilon, and these are plus minus 1. I have these, if you like, Fourier coefficients, V tilde, which depend on the position of the charges. And then we have the Fourier factor e to the I square root beta sum I is equal to 1 to n phi xi sigma I. So I want to write the potential V or Vt always in this form. So in terms of some functions which are to be defined, these V tilde, so these functions, I haven't defined them, but I want to define them in such a way that the potential is given like this. Two remarks. If you compare with the so this, okay. Let me point out. So you might want to put might be natural, or it is in fact natural to put a factor epsilon to the 2n here, normalizing these sums as integrals. But here these just go into this v tilde. So this is the microscopic rather than macroscopic point of view. So these are considered. So these are considered part of v tilde. So v tilde is going to be small rather than singular. The second one is okay. So these xi's, I guess. So psi I always denotes xi sigma I. So these are thought of as n charges with positions xi and charge sigma I. And thirdly, this vn, this v tilde is really a function that depends on n. But so really maybe we should have put an n here. But usually I will not write that n because that n is obvious from the number of arguments I'm plugging in. Okay, so I want to write v in this form. Now the initial so our initial potential certainly has this form. In fact, a very simple way, v tilde of 0. So for n is equal to 1, so there's only one charge, is just given by z naught, some constant, where this constant is this epsilon to the 2 minus beta over 4 pi times z, where z is the coupling constant that appears in the definition of the model. And all other ones are 0. So this is the our initial interaction, our initial potential, parameterized in these, if you like, sort of Fourier variables, or okay. You see that this representation has something to do with the Sine-Gordon transformation and the Yukaba gas representation, and in fact, what we'll see is that these v tilde t, or we won't see it, but it's true. This is in fact what Bridges and Kennedy did. They showed that these v tilde tn's are in fact the Ursel functions for the Meyer expansion of a regularized Yukaba gas. But we won't need that, so don't be scared if you don't understand what that means. Okay, so we have the initial condition, and we want to know we want to solve the Pulzinski equation. The Pulzinski equation, let me recall, is this equation. So here, in the discussion of the Log-Sobolev inequality, I was always very careful about distinguishing arguments t and s, using t for time and s for scale. So s was the sort of time variable used in the Pulzinski flow, while t was the time variable in the Glauber flow. Now I'm going to need two variables in a lot of places, and since there's no Glauber flow involved anymore at this point, I'm going to drop that convention and use t and s interchangeably whenever. I mean, I usually need two, and so I don't always want to write s prime. So I'm going to use t also. So we want to also here. So we want to solve this this Pulzinski equation. Okay, and so remember Ct dot is just e to the minus ta, where a is the Laplacian plus a mass term. So what we're going to do first is we're going to rewrite the Pulzinski equation in this representation as an equation for the v tildes. So that's like writing an equation in Fourier space rather than in real space. So it's the same principle. So we're going to do that. Okay, so maybe I'll copy this to the next slide. Okay, so there's two terms on the right-hand side. So let's start with 1. So let's say 1/2 Laplacian Ct dot v phi is, I want to write it as 1 over n factorial times the sum over psi 1 up to psi n. And then I'll write VC dot V tilde. So this is now sort of the corresponding Fourier coefficient, which depends on n arguments. So there's a sum over n missing here. So I guess it should be a sum over n. And then there should be the Fourier factors. Okay, so so what is this this quantity? So what is that? Well, you can check that if you just use so in this kind of Fourier representation, the Laplacian becomes a multiplication operator, as it does in the ordinary one. So this is minus, so maybe we put a half here just to match my convention. So this is minus beta. Maybe I'll put one, let me put the half here. So then some I, maybe j, k from 1 to n. Then there is a beta sigma j, sigma k, c t dot of xj, xk. So this whole thing is multiplying v tilde of psi 1 up to psi n. Okay, so what am I claiming here? Well, I'm claiming if your function v is given as on this slide, right? If it's given as a sum over n from 0 to infinity of these functions vm, which have this sort of Fourier type representation, then when you apply the Laplacian, well, that result has the following Fourier representation, where this Laplacian v tilde is given in terms of this this formula. So basically, you differentiate twice in the exponential here. You bring down two factors of I square root beta, so that's a minus beta, and you bring down these terms, these sigmas here, and they are connected by the covariance here. So that yes.
Perhaps the indices are not right. There's a k probably somewhere.
Oh, yeah, so there should be a k of, and this should also be a k. Thank you. Okay, so, and I will call this maybe w dot t, and it depends on psi 1 up to psi n. So in other words, so this Laplacian becomes a multiplication operator in this representation. And now we have the nonlinear term. So the quadratic term, that one will not become a multiplication operator. So we want to express the Fourier coefficient of this gradient v squared. So what do I mean? Again, the same thing, that if v is given, sorry about this. So if v is given by the representation, by the formula from the previous slide, then if we take this combination gradient v squared, that is given as the sum in terms of these coefficients, which I'm about to define for you. And how are they given? Well, they're given you. So here you'll have two copies of v on the right-hand side, right? And so let me write down the formula, and then we'll see why it may be true. So we sum over subsets I and I1 and I2, which are disjoint, and whose union is the interval from 1 through little n. And then I'm summing over indices. J is in the first set and K is in the second set. And then we'll have a again, there's a beta because we're differentiating twice. So we'll get 2 factors of square root beta. And then we have the C dot of T xj xk sigma j sigma k. And this is multiplying V tilde of psi I1. And I will explain what that is in just a second, psi I2. So, okay. So here, psi I1. So we have 2 subsets, I1 and I2. We have this vector psi. So by psi I1, I mean, this is the vector. So it's a vector indexed by I1. So it's psi I, where I is in I1. So it's somehow, it's a sequence of absolute of the of k variables psi 1 up to psi k, where k is the length of the interval, or is the number of points in I1. And similar and analogously for I2. And then we have this prefactor here, which I'll abbreviate as u dot of psi j, psi k. So this is, okay, so this is the kind of formula. I'm not going to do the more detailed computation for this because it won't help you very much. I mean, it's either you see it directly or you have to check it, but this is the result what you get. I mean, you can see roughly that this formula is reasonable. You're differentiating V, well, you're differentiating V, so each factor of V is connected to a covariance here. The 2 V's are, so you get something quadratic in V, that's also reasonable. And then you sum, roughly speaking, over all possibilities to connect the differentiations of the different variables. That's basically what's happening. Okay, so anyway, this is the formula that that gives you a gradient V squared, the Fourier coefficient for gradient V squared. And so now we can write the Pulzinski equation in Fourier space. And so that is just, we take the derivative of V tilde, depends on n arguments. Then we have the Laplacian term, which is minus W dot T, just multiplication operator. And then applying to V tilde T, psi 1 up to psi n. We have one of these equations for every n. And then we have the nonlinear term, which is given by 1/2 times, okay, I should, let me write this out first. So minus 1/2 gradient V tilde. Okay, so this is the equation in Fourier space. Now so this tilde is including the square. Now I can try to solve this by writing down the Duamel formula. So looking at the corresponding integral equation. The corresponding integral equation is V tilde T, again for psi 1 up to psi n. We get e to the minus Wt psi 1 up to psi n times V tilde T psi 1 up to psi n. So here note this WT doesn't have a dot on it, right? So what does it mean? Well, it means take W dot T and integrate from 0 to T. And then we have the nonlinear term, which gives...
you probably mean V of 0 on the right-hand side, no?
Indeed. Thank you. And then we have the integral, which is e to the minus W of T minus S Xi1 up to Xin. And we have this sum over the subsets I1, I2, and J is in I1, K is in I2. And then we have this U dot S of Xi J, Xi K. And we get these two V tilde S of Xi I1, V tilde S of Xi I2. And then there's a ds. Okay, so this is the integral formulation of the Pulzinski equation in terms of these coefficients. And so let me make a couple of remarks. First of all, so here we're looking at n. I'm going to refer to these variables as particles because really these are particles in the Yukaba gas picture, right? So here we're looking at n particles. And on the right-hand side, we see that the V tildes involved, well, they are V0 at all n particles. Okay, we know what that is. And then it's Vs tilde, but only at n minus 1 particles, because here we're taking V tilde S evaluated at Xi I1, where I1 has a disjoint union with I2 to be given by n, and each of these two sets, I1 and I2, are not empty in the sense that one of them has to contain J and the other one has to contain K. So these two only involve n minus 1 particles at most. So depend on, at most, n minus 1 particles. So since these two sets, I1 and I2 are not empty. So what does that mean? Well, it means one can just get a solution to these integral equations by induction. So if we look at just n is equal to 1, well, then if n is equal to 1, that integral actually doesn't contribute because there are no two subsets that are disjoint and non-empty that form that both give one whose union gives one element, right? You get at least two elements. So that integral doesn't contribute. You just get the first term, and the first term is easy, right? We only have one particle, so we just get e to the minus wt Xi1 of v tilde 0 Xi1. And remember what W was. This is just e to the minus beta over 2 CT 0, 0. And then it's V tilde of Xi1, which we called Z naught. If you remember, that was some slides back here. We just called that Z naught. On the other hand, we see that at time 0, or scale 0, all the other Xi's are actually 0, right? So that means for n at least 2, the first term actually doesn't appear. It's only the second one that appears. So for n greater than 2, it's only the second one that appears. So I guess we can, that is one of the advantages of doing this on a tablet as opposed to a board, that I can just copy this. Okay, so, all right, so we know what these Fourier coefficients are for n equals 1, and we have an explicit formula for all other n in terms of the lower ends. So for example, we could just go ahead and compute v tilde for 2 particles. And it would be, it's an explicit computation, and you just get a formula, and then you can use the formula you have for 1 particle and for 2 particles to compute it for 3 particles and so on. So by induction, v tilde t for xi1 to xin is always defined. Second remark is, okay, so this is maybe a side remark. This is what Bridges and Kennedy, among other things, noticed in their paper, is that these v tilde t's are in fact the Ursel functions we won't need it, but anyway, it seems like a fun thing to observe of a regularized Yukaba gas. And then going back to, this is more of a side remark, maybe I'll put this at the bottom. Anyway, so something else we want to know is that, well, so I've explained that we can always define these v tilde t's for all arguments. So far, so good. But there is a little bit of a gap in what I've explained so far, because so those will give solutions to this system of integral equations, if you want, or to this system of these equations for the Fourier coefficients. But really, what we want is a solution to the Pulzinski equation in the original phi space. Now, if you have a solution for these Fourier coefficients, well, then to get a solution to the Pulzinski equation, what you need is that these sums actually converge, and let's say absolutely. So if these solutions we find by induction are such that these sums here converge absolutely, then in fact you can take this, differentiate it, and check that it's a solution to the Pulzinski equation, and these are unique. So so if the series star, which is this one, probably used star before, well, maybe not. So if that one converges, let's say absolutely, then it gives the unique solution to the Pulzinski equation. And in fact, in that case, it also gives good estimates on the Pulzinski equation, because you can, if you know it converges absolutely, the way we'll see that it does is we'll get estimates on these coefficients, and so that those will also give good estimates on the solution to the Pulzinski equation. So what we'll do next time is we'll derive some estimates on basically on this equation, and for beta less than 4 pi, it's very simple to do that. You can just do that by induction. We know, as I explained, we know what happens if n is equal to 1, and by induction we estimate all the higher ones in a fairly crude way, and get bounds on these coefficients, which then give the solution to the Pulzinski equation. okay, so one way you could interpret this is some kind of existence theorem in a space of analytic functions. So we have these Fourier coefficients with good bound. We'll have these Fourier coefficients with good bounds on the coefficients, and it's some sort of very well quantified Cauchy-Kovalevsky argument or something like that. Anyway, so that's what we're going to do. We're going to estimate these coefficients and see that the bounds are good to, at least with beta is less than 4 pi, that they're good to get a solution to the Pulzinski equation. And then we're pretty much done, because we'll be able to get estimates that allow us to check the criterion in the needed for the Log-Sobolev inequality. There's a few points that I'll explain a bit more detail next time. I don't think we'll have much time for this right now. But so, for example, let's say if we stay for beta less than 4 pi, you see the cancellation of the counter term already in this equation for n is equal to 1, right? So this z naught was given by epsilon to the 2 minus beta over 4 pi times z. So it has this counter term epsilon to the minus beta over 4 pi in it. So relative to the macroscopic scale, this looks huge. It looks small microscopically, but macroscopically it looks huge. So macroscopically you lose the factor epsilon squared. On the other hand, so what we'll see, or is easy to see from this, and we'll do this in detail next time, is that so here you just see the effect of doing the Gaussian integral, which basically just cancels that counter term there to as t becomes macroscopic, which is in my normalization here of order 1 over epsilon. So you can see in a completely explicit way how this counter term is just canceled at this linear level, and up to 4 pi, that is enough to pull through to get these nonlinear estimates on the nonlinear equation. If you cross this threshold of 4 pi, things get a bit more subtle, because then it is in fact not true that the estimates will become more subtle, and I'll try to give an indication of what happens exactly then, and presumably at the higher thresholds as well. Okay, so I think my time is up, and we'll continue from here next time.
Okay, thank you very much. Maybe we can all upload. Are there any questions?
I have one.
Yes.
I mean, the way you set it up with this particular way of organizing your Fourier decomposition for V is, of course, super convenient, because your initial condition is so super simple.
Yes.
How does this look if you look at different potentials? How flexible is this?
Okay, I think you could, I think it wouldn't be a problem to allow, say, finitely many Fourier coefficients non-zero.
Say 5 to the 4.
Sorry?
Say 5 to the 4.
Well, 5 to the 4 we cannot write in this so here we're really heavily using this Fourier representation to get good estimates. So what you're asking is about well, let's see. You're asking about this, right? How do we?
Possibly. I'm just wondering. I mean, 5 to the 4 should, in principle, also have such a representation, just not so explicit, no?
Well, I mean, so not really. I mean, so this okay. Representation we're using here is very specific to the periodic case, right? It relies on the fact that the potential is periodic.
Mm-hmm. I see.
But indeed, as you say, it would be very interesting to check this for 5 to the 4. I don't know how. My feeling is that it should be it should be doable. It shouldn't be too hard, but it's not. It's harder than the Sine-Gordon case that I'm explaining to you, for the reason that, well, for phi-4 you need to get a lower bound on the Hessian, and the upper bound is not going to be true. For Sine-Gordon, we'll be able to bound the Hessian from above and below because it's sort of it's bounded. It's sort of symmetric, and it's always easier to bound something from above and below rather than just from below, right? So, but anyway, it's yes. So I mean, there's my feeling is that this should be true for phi-4, but I'm not sure how to check it. I mean, there's these. I mean, you and Pavlov has this proof of the spectral gap, which is sort of good indication that one might hope it's true. There's these works of Barashkov and Gubinelli, which use not exactly the Pulzinski equation in exactly the same way as we do, but are very closely related in spirit. There's also, I saw there's a recent paper by Wang who uses something along the spirit for phi-4 too. But I mean, getting the estimate on the Hessian, I guess, is a different problem than constructing the measure. And so far, I don't know how to. Anyway, good problem.
Okay, there is a question in the chat.
Can you comment on the difficulty? Well, I'll do that next time. So the question is, can I comment on the difficulty when beta is bigger than 4 pi? I can comment on that next time. So it's you can see that very. I mean, so one of the beauties of this representation is you can see very explicitly what the issues are, and that's also part of the part of the restriction that that it's a bit too explicit. Yeah.
Okay, if there are no other questions, then we can thank Roland again.
Sorry, I was too slow at typing. Can you comment on the estimates independent of the volume? I couldn't see it in.
Yeah, well, I haven't stated the estimates yet. But basically what you'll see is that, so, I mean, the way, okay, so that we'll see next time. So the way these coefficients V are estimated in terms of estimates on these coefficients. And these involve sums over all but one argument. And these sums, they're just uniform in the volume because they're basically restricted to, say, arguments which are in an, go up to order square root t or something like that, in a radius over balls of a radius of square root t or so. I mean, so that you'll see that once this series converges, we'll have estimates that are uniform in the volume. So and that series will converge in this region. So under this small coupling assumption. Now, when we're in this theorem, I also stated a result that is not under the small coupling assumption, and that's actually, in that case, actually that series will not converge. But what as I'll explain, what we can still do is we could still run it up to a certain time, t0, which is already macroscopic, and at that point the potential is smooth, and then you can go from that scale, t0, to the final scale, where this expansion doesn't converge anymore. But okay, so you can basically use the maximum principle to go from that macroscopic scale to the rest. It's sort of something like the Holy-Struck argument. Once it's become macroscopic, you can conclude and works uniformly in epsilon. You'll get bounds that are not good in L. They're probably exponential in L or something like that, what you typically get by these types of arguments.
Okay, thanks.
So I have some questions, if I can. So first one, it's so from your approach, proving Log-Sobolev and proving Poincare inequality seems to be of the same difficulty, basically, no?
Yes.
Another thing is, I like a lot your approach, but I having a terrible time trying to adapt it to discrete spin models.
Okay, I guess it depends a bit on, I mean, okay, so we, it's related to this approach, but it's much simpler. We had a very short paper, it's only 4 pages or something like that with Thierry, which is called something like, look, or very simple proof, of the LSI for high temperature spin systems or something like that. And there we also look at Ising and discrete systems. Basically what you can usually do is, so with this heat kernel, it's a bit inconvenient, but and that, so what you can use is a decomposition, which is, let's see. So in general, we want to decompose the Gaussian measure in, where is it? Oh, it's even further back. Here it is. So so the heat kernel decomposition, as I explained, is particularly, seems to be particularly nice and gives particularly sharp estimates. But in principle, you could have some decomposition that C dot S prime that is a bit different, right? And so one of them that one could use is a so-called finite range decomposition. So what that means is C dot S will, so here it's a heat kernel, so it has like a Gaussian tail, roughly speaking. But you could use one that has let's say, a finite range tail. You can do that. And so in particular, what happens from scale 0 to 1 is IID. The range is at most 1, but it's just, I mean, the range, if you're on a lattice system, is discrete. So it's going to go at most, well, it has to be less than 1, but it's discrete, so it has to be 0. So basically, you'll have a short time interval for which the range is 0. And that basically smooths a discrete system to a continuous one. And from that point on, it looks the same as this. So we use this, for example, for the Ising model or the discrete Gaussian model in another paper on the hierarchical models, where so somehow the discrete nature of the systems didn't really matter for, I mean, we use this trick to have from time 0 to 1, you have the scaling, you have the smoothing effect, and then it's continuous. And I'm not sure how, yeah, I mean, so those systems are probably simpler than what you have in mind where we tried this, but in principle, there's something you can do.
Okay.
I'm not sure if I answered your question.
No, it's okay. I mean, at least it's something to look after. Of course, as you may imagine, I'm more interested in Kawasaki, and then it's more complicated. But
yes, indeed. Okay. Yeah.
Yeah. Anyway, thank you.
All right. If there are not any more questions, then we will resume at 3:15.